Bismillahirrahmanirrahim, dear students. Grade 11, chapter number 8, and we are talking about the buffer solutions today. Now, lecture number 56 and buffer solutions. Buffer solutions are those solutions which maintain and resist to change their pH. Buffer solutions are those solutions which maintain or resist to change their pH after addition of small amount of acid or base are called buffer solutions. Means they keep their pH for a long time. When you add acid or when you add base small quantity, they are not going to change their pH. Mostly the buffer solutions are prepared weak acid, salt of strong base. Weak acid and salt of strong base. So when you use a weak acid, the very important buffer solution, acetic acid, weak acid, salt of strong base, sodium acetate. Very common buffer solution. Here the common ion also. Acetate is a common ion. So when you use a weak acid and salt of strong base, these are called acidic buffers. We call it acidic buffers. But when you use weak base, this is a weak base, and salt of strong acid, salt of the strong acid, ammonium hydroxide, ammonium chloride. There is also common ion, ammonium and ammonium. These are called basic buffers. Acidic buffers and basic buffers. Weak acid, salt of strong base, and the weak base and salt of strong acid. Don't use strong acids and strong bases. No buffer is going to be remain buffer for the long time. So they are going to be resist the change of pH. So there are many examples also. You can use hydrogen fluoride, which is weak acid, and sodium fluoride is salt or strong base. Many other buffers you can use. Carbonic acid, phosphoric acid you can use for this purpose also. There is one thing that in the definition I told you, when small amount of acid or base are added in the buffer, the pH of buffer is not going to be changed or very slightly changing taking place. Buffer remains the buffer. Suppose any solution you can use. This is the acetic acid, and this is the salt of strong base. This is the buffer. You prepare this buffer solution and you want to check that this buffer solution is a good or not. It maintains pH or not after addition of a strong acid. This is a strong acid, hydrochloric acid. The very strong acid, small quantity, very small portion of the acid, the hydrochloric acid is going to be added. Its pH is near about 0.1. It's a very strong acid, so we expect that when you add HCl here, so its pH should be decreases because it's very strong acid. Hydrogen ion concentration is going to be high, very high when you add in water because completely ionized or dissociate. So when you add the acid here, so it's expected that the pH of buffer solution which prepared already is going to decrease. because a strong acid's pH is very low, 0.1 like this. But there will be no change or very small change taking place because this is the acid and this is acid, no reaction. This is salt of strong base. Reaction with the hydrochloric acid, you will get acetic acid again and you will get sodium chloride. This is the product. This acetic acid does not react. Sodium acetate, negative, positive, positive, negative. They are in aqueous solutions. So this negative acetate radical react with the hydrogen, negative and positive to give acetic acid, and this positive and the chloride negative to give a sodium chloride. This is a product. The students, acetic acid is already present in the solution, only the volume, the concentration, moles of acetic acid will be increased in the buffer. Acetic acid is the 1 mole, 2 mole, 3 mole, 100 moles, 1000 moles. But the pH will be same. pH will be same because only the volume, only the number of moles of acetic acid are going to be increased. So no effect on the pH. And sodium chloride is a neutral salt. Sodium chloride is a neutral salt. We will discuss in the next topic, salt hydrolysis. So that's why it does not change the pH. Very slightly, little change or no change taking place when you add very strong acid. Now I'm going to add a base. Again, this is a buffer solution. And now, suppose I am adding sodium hydroxide. Sodium hydroxide is an alkali and very strong base and pH near about 14, 13, 14. Very strong alkali, very strong base, dissolved in water, give erythrolytic reaction. So its pH should be elevated, increase up to 13, 14 because you are putting highly strong base and 100% iodized hydroxyl ions in aqueous solutions must be increased. But you will see that there is no increasing of the pH because this is a salt of a strong base and this is the base, they don't react. This is the acetic acid and this is the sodium hydroxide, they can react with each other. So there is the acetic acid, negative charge, and hydrogen positive charge. Sodium is a positive and the hydroxide are negative. So this positive react with the negative acetate, you will get sodium acetate. Concentration of the acetate ion is going to be increased. Common ion is going to be increased, sodium acetate is. So sodium acetate already present in the solution. Sodium acetate is already present in a solution. And this is the hydrogen and this is the OH to make a water. So we prepare all solution in water, aqueous solutions. So that is why sodium acetate is there, sodium acetate is there. So no effect on the change in pH of the buffer solution. That's why I told you when you add a small quantity of acid or base in a buffer solution, any buffer solution, because this is a very common and very important, very famous buffer solution we use. That's why I put this one. So there will be no change in the pH of the buffer solution. Now here numericals are given here. Buffer solutions and their applications. I am going to solve numerical. Calculate the pH of acetic acid sodium acetate buffer solution containing 1 mole of each component. So here you have the same buffer solution and concentration is a 1 mole each, like this one. And you have to use the formula Ka ionization constant for acid is concentration of the acetate if you dissolve in water according to law of mass action, concentration of hydrogen ion and the concentration of acetic acid. This is the formula you have. So concentration when you calculate the pH, I should have the hydrogen ion concentration. So Ka value is given for the acetic acid. This Ka value is given in the book 1.85 into 10 raised power minus 5. This is a Ka value. So Ka is given 1.8 into 10 raised power minus 5. Concentration of acetate 1. We are going to calculate the hydrogen ion concentration, and concentration of acetate is also 1. So that is why if you are going to calculate the hydrogen ion concentration, so this is hydrogen ion concentration 1.8 into 10 raised power minus 5. pH is equal to minus log of hydrogen ion concentration. So put the value. Yes. So this is a minus 5. So log of 5, this log power is gone. You will get 5 here and minus log of 1.8. So 5 minus log of 1.8, then you will get a pH 4.745. So this is a pH of the buffer solution. pH of the buffer solution. Now, what will the pH of this solution after addition of 0.01 mole of hydrochloric acid to 1 decimeter cube of solution? Assume that volume of solution remains unchanged and the value of K is given. Second part of this question. Second part. So students, when you add more HCl, I told you when you are going to add the HCl on sodium hydroxide, very small change in pH takes place and the buffer solution act as a good buffer. Now I am going to change the concentration. Now HCl I am going to add 100% ionization. I add this in the buffer solution. So the HCl concentration is going to be 0.01, small amount of HCl you add. 1 mole of this one, 1 mole of this one is 0.01 and 0.01 m. Like this. So dear students, when you are going to write components of the buffer, acetate ions, hydrogen ions, to make acetic acid in aqueous solution must. So concentration of acetate ions we add 0.01. Hydrogen also 0.01. Acetic acid also 0.01 because 1 mole. 1 mole here. Now you have concentration of acetic acid original, it was 1, and concentration of acetate also 1. So dear students, when you are going to acid, this is very important to know, when you add acid, the concentration of hydrogen is going to be increased. So this is the acid, so you have to add 0.01 here. But this is acetate, the conjugate base. This is the base, conjugate base, and you are putting acid here, so should be subtracted. This is the technical point, you must know. This is the acid and this is the acid, that's why you add this one, this is the base, must be subtracted. So you will get, after addition and subtraction, you new molar concentration. So molar concentrations are, after the addition, 1.01 mole, and here is a 0.99 moles. So apply the formula same. Ka is equal to concentration of acetate, concentration of hydrogen, and concentration of acid, like this one. K value is same, 1.8 into 10 raised to the power minus 5. Now concentration of acetate is 0.99 moles. We want to calculate the concentration of hydrogen ion. Divide by concentration of the acid is 1.01 like this. So when you are going to calculate the hydrogen ion concentration, then your formula will be 1.8 10 raised to the power 5. It is going to be numerator here. Multiply by 1.01 divided by 0.99, then you will get the hydrogen ion concentration. That will be 2.2 into 10 raised to the power minus. Please calculate yourself by using calculator. If there is a variation, then you please correct it. 2.2 into 10 raised to the power minus 5. This is the hydrogen ion concentration. So pH is equal to minus log of hydrogen ion concentration. So solve this by using this. So you will get 4.736. So dear students, before, when we not add concentration 1 each, the pH was, when we calculate before, 4.745. After addition HCl, 4.736. So change in pH is a very small. After addition of the hydrochloric acid, the pH is only difference. The difference is a very minute, 0.009 about. Use your calculator and calculate the difference of the pH. So very small difference I told you. If you add the very strong acid in the buffered solution or very strong base in the buffered solution, so you will see very small, minute change. It is going to be decreased. The pH is going to be slightly decreased, 4.745 to 4.736, and this is the change. So buffer is going to be good buffer. It is doing very good job because there is no significant change in the pH after addition of very strong acid. So please do at home. When I add 0.01 m of the sodium hydroxide. What will be the change in pH in the buffer solution when I add 0.01 mole of sodium hydroxide? I am giving you a hint here. That if I add sodium hydroxide, write this equation, then please 1 plus 0.01 for the acetate and 1 minus 0.01 because you are adding base, so this will be subtracted. Then you have to do this one and now see what will be the change in pH. Already I told you there will be no significant change in pH after addition. So that's why the buffer solutions are those solutions which they retain their pH. There's no change in pH. Applications. Buffer solutions play an important role in several industries' process. They are used in the manufacture of photographic materials, leather and dyes coloration. They are used also process of electroplating and analytical procedures. Buffer solutions are also used for the calibration of pH meter. I told you that when we have different solutions, different soils, we are going to check the soil that which means crop is suitable for that soil. After analyzing that, we have to check the pH. So either we use the pH paper or we use pH meter. pH paper will give a rough result, not a 100% accurate result. It is the very light yellowish orange paper, small, is to put in the solution. If it's going to be red, acid is going to be blue, that is called base, and the scale is given on the top of the packet, and the colors are given from 0 to 14 pH. After dipping in the solution, they match. So roughly you have idea that what will be the pH of that solution. But if you want to measure the accurate pH, then we use the pH meter. So when we use pH meter, different solutions, so maybe this instrument gives some error after using. So that's why we have to calibrate by using known pH. So we buy the known pH buffers. Mostly we use 7 and 14 small capsules of buffer solutions. Written on that this is the 14 pH buffer solution and this is the 7 pH buffer solutions. Put in the distilled water, make a solution. It is standard. It is given that this buffer is a 7 pH. Then you have a pH meter and there is an electrode, very highly sensitive electrode, calomel electrode in the pH meter, very sensitive, highly. So just you are going to first clean it with distilled water. There should be no previous solution present in the electrode, the highly sensitive, maybe here come. You have to clean with the distilled water 2 or 3 times. Then put in the known pH buffer 7 or 14. So when I put this electrode, dip in electrode in the known buffer solution, if readings 7 in the pH meter, it means that your pH meter is already calibrated or it is going to be okay. Then you can use for unknown solutions. But every time you must must clean the electrode by using a distilled water, that previous solution not present in the electrode. So if it gives different pH, more than 7, less than 7, but you know the 7 of a buffer solution pH is 7, so you have there a small, here is some knob button, there is so you can move it and you can adjust the pH 7 according to your solution. So this is the calibration of pH, that you can calculate the accurate pH of the samples. In nature, many biological systems depend upon buffer solutions preserve constant. There is one thing very important. Human blood. Human blood is an excellent buffer. The pH of the human blood is not going to be changed. Remember that it maintains 7.35 to 7.45. Must remember it. Human blood pH is between 7.35 to 7.45. You are taking medicines, you are drinking soft drinks, you are drinking lemon juice, orange juice, acidic bases, eating many times other things you are eating and drinking, but your blood pH is not going to change. If change, no survival, death takes place. Very dangerous. So that's why from Allah, whatever maybe you eat, the pH of your blood maintains 7.35 to 7.45. It's a very good or excellent buffer. Tears 7.40. Gastric juice, stomach juice, pH 1.65 to 1.75. Fresh milk 6.7 to 6.8, near to neutral. Protein, egg protein white 8 to 8.1, very slightly basic. They are going to be calculated by using the pH meter. Buffer solution are to maintain the pH of the culture media for the growth of bacteria and the bacteriological applications. So dear students, these are the applications of buffer solutions. I explained the buffer solution and their applications. Now students, next topic is salt hydrolysis. One hint I am giving you to solve the numericals here. Dear students, may become this not included, but I am giving you a hint, very important. If you see your book, example number 11, what the pH of buffer solution? You have acetic acid, 0.1 moles per decimeter cube, and the sodium acetate, again 1 decimeter cube, 0.1 for the acetic acid, 1 of the sodium acetate, and the pKa value is given. So, dear students, I am writing the equation. You must remember, may become this, may not be because not included, but I am going to give you idea about this. You have this buffer solution, and the concentration of the acetic acid is 0.1, and the concentration of sodium acetate is 1 mole, and pKa value is 4.76. If Ka value is given, then pKa is equal to minus log of K. You can calculate the value of pK by using this formula. So, dear students, the formula is used, we call Henderson's equation. We use Henderson's equation. This Henderson equation is pH. We want to calculate pH of the buffer. If these concentrations is given and this is the pK value. So pH is equal to minus log pH is equal Henderson equation pKa plus log of concentration of salt, means this acetate is concentration of salt divided by concentration of acid. Simple. So please do this. Remember also this one may become pK value is given 4.76 log of salt. This is the salt 1/4 log of the acid. So divide, take a log plus, you will get the answer pH. So you can calculate this, and sometimes they say that after addition of 0.01 for the acid, for the hydrochloric acid, or by addition 0.01 for the sodium hydroxide, for the change in pH, then you have to use this again to calculate this one. So this formula I am giving you for the calculations. Same activity for the students. pH same 0.11 molar sodium acetate and 0.09 acetic acid. Ka is given, change into pK and calculate this one. So this is about the buffer solutions. So just I am going to give introduction in detail in next lecture. Salt hydrolysis. Salt, ammonium chloride salt, positive one and negative one. Hydrolysis, react with water, bond broken down to give acid and base is called salt hydrolysis. Salt, ammonium chloride salt, react with water to give ammonium hydroxide and hydrochloric acid. So the purpose for doing this, dear students, we have acids and bases. Sodium hydroxide base, hydrochloric acid acid. Some oxides, non-metallic oxides, they have the acidic behavior, and metallic oxides have the basic behavior, and some aluminum oxide, this is the amphoteric oxide. But the salts, they have also acidic and basic nature, and also neutral. Salts means if you have different kinds of salts, 3 kinds of salt A, B, C, and you are putting in the water, and you have the litmus paper, so you can put, they change. One salt that change blue to red, and other salt may change red to blue, and third salt no change. Means the salts also have the property of acidic, basic or neutral. So by using this technique, salt hydrolysis, we will be able to identify that what is the nature of the salt. That's the, just I am giving introduction. In the detail, there are the scientific reasons. Scientifically we have to calculate, but this is a general. Ammonium chloride is salt. So from this I can say that this salt has which nature? Acidic, basic or neutral. After hydrolysis, I told you will get acid and base, hydrochloric acid and base. But you should know, after the formation of acids and bases, you must know that which one is a strong, which one is a weak, or both are strong or both are weak. You must know the nature. If you don't know nature, then you can't decide. Hydrochloric acid is strong acid. Ammonium hydroxide, weak base. Now I can. Weak base means hydroxyl concentrations are small, less, and hydroxyl concentrations are more. So when the hydrogen ion concentration are higher, larger in the aqueous solution as compared to the hydrogen ion concentration, The nature of the ammonium chloride in water is acidic. So ammonium chloride in aqueous solutions has an acidic nature because it gives strong acid and weak base. Strong acid and weak base. Strong acid means hydrogen atom concentrations are greater, larger than that of the hydroxide ion concentrations. Other example, then I will stop here. If you have sodium carbonate, same sodium positive 1, carbon negative 2, hydrogen positive 1, OH negative 1. So you will get here sodium hydroxide and carbonic acid. You must remember, you must have this practice. So sodium hydroxide alkali, very strong base. Carbonic acid, carbonate brings weak acid. So we have result now. A strong base, hydroxide concentrations are greater than that of the hydrogen ion concentration because weak base does not dissociate, very small dissociation. So aqueous solution of sodium carbonate is basic nature. So we will do this one. Same for the neutral also. Sodium chloride will give you neutral. Sodium nitrate give you neutral. Sodium sulfate neutral. Potassium nitrate neutral because they give the strong acid and strong bases. So dear students, we complete here. Inshallah next lecture I will give you a detailed lecture about this, how they act as a acidic, basic and neutral. Thank you very much.